Now, next topic, that is continuous charge distribution. It implies that suppose we have a system of charges in which the distribution of charge that is continuous one. Then due to that particular continuous charge distribution, what will be the electric field at any point outside that charge distribution that we want to find. So let's first consider the linear, or we can say line charge distribution. Suppose as shown in the figure, on this particular line, charge is continuously distributed. And due to this particular charge distribution, we want to find the electric field at point P having position vector r with respect to the origin of Cartesian coordinate system. Suppose the linear charge density on this particular line charge distribution, that is lambda. Linear charge density means charge per unit length, that is lambda equal to total charge, suppose that is Q, and total length is L, then we can write lambda equal to Q by L. Its unit will be coulomb per meter. Now, the concept here that we have to use like this, we have to divide this entire charge distribution into so many infinitesimal small line elements, so that each line element can be treated as a point charge. Then due to each one, if we find out the electric field at point P, and then after take the vector summation. Suppose one such small element dl dash is at position r dash with respect to the origin, and the charge residing on it, that is dq. So due to this particular dq charge, the electric field at point P, that is dE, equal to k dq upon magnitude r minus r dash cube into vector r minus r dash. Now, this charge dq that is on the line element dl dash, now linear charge density, that is lambda. So we can say charge per unit length is lambda. Therefore, charge on length dl dash is how much? So dq will be lambda at r dash into dl dash. Now, this one is the continuous distribution. So here we can calculate the resultant electric field at P by taking the integration of this equation. So resultant electric field E, that is equal to K integration. Integration should be carried out over the line. So integration over line lambda at r dash into dl dash upon magnitude r minus r dash cube into vector r minus r dash. So this one is the resultant electric field at point P. Now at point P, if any charge Q is placed, then simply we can calculate the force acting on it, that is Q into this E. Simple thing. Clear? Now surface charge distribution, the concept is the same one. Suppose here as shown in the figure, for this given surface, the total charge residing on the surface is Q and the total area of the surface is A. So here we can write surface charge density, that is sigma, equal to Q by A, unit will be coulomb per meter square. Surface charge density means charge per unit area. Now, here divide this entire surface into so many infinitesimal small elements. Due to each element, calculate the electric field at point P having position vector R. And then take the vector summation of all, we will get the resultant one. So suppose here one infinitesimal small surface element, that is dA dash. Suppose the charge residing on it, that is dq. So due to this dq charge, the electric field at point P, that is dE equal to k dq upon magnitude r minus r dash cube into vector r minus r dash. Now dq is how much? So per unit surface area, the charge is sigma. Therefore, on the given area dA dash, charge is how much? Simple unitary method. So we can write dq, that is sigma at r dash into dA dash upon magnitude r minus r dash cube into r minus r dash, k as it is. Now, to find out the resultant electric field at P, take the integration of this equation over the surface. Clear? So E, that is equal to K integration over the surface sigma r dash magnitude dA dash upon magnitude r minus r dash cube into r minus r dash. Clear? Now, third, that is volume charge distribution. Suppose, as shown in the figure, we have the volume V in which the charge distributed, that is Q. Concept is again same one here. First of all, we have to consider infinitesimal small volume element, and suppose that element is dV dash situated at position r dash from the origin, and charge residing on it, that is dq. Now, due to that, first of all, we have to find the electric field at point P having position vector r, and then after take the integration over the volume. So here, first of all, we have to take volume charge density, that is charge per unit volume, that is total charge upon total volume. So Q by V coulomb per meter cube. Now, electric field at point P due to charge dq, that is k dq upon r minus r dash cube into r minus r dash. But again, now dq, that is volume charge density into volume dV dash. So dE, that is k rho at r dash magnitude dV dash upon magnitude r minus r dash cube into r minus r dash. Now take the integration of this one over the volume. So electric field E, that is equal to k integration rho r dash magnitude dV dash upon magnitude r minus r dash cube into r minus r dash. So in this way, one can find the electric field at any point due to continuous charge distribution. Clear?